Hey everyone, and welcome to today's Explainer. We've got a really fascinating engineering mystery lined up for you, sourced straight from a curious learner's question. We're going to be digging into variable frequency drives, or VFDs, and a very specific phenomenon that honestly trips up even seasoned electrical engineers. So grab your virtual hard hats because we are going hunting for a missing sine wave. So here is the paradox we're dealing with. In a standard VFD setup, our input is alternating current, right? It's a beautiful, completely pure sine wave. And our output? Well, we're using alternating current to drive the motor at the very end of the line too. So if we feed a pure AC sine wave into a VFD and we get AC out on the other side, what exactly is happening in the middle to distort it? Why don't we get a pure sine wave at the output? It's an absolutely brilliant question, and to solve it, we need to head straight to the scene of the crime. Okay, let's dive into this with Section 1, inside the VFD process, tracking the current. To figure out where our pure sine wave vanished to, we essentially have to play detective and systematically track the electrical current as it moves through the variable frequency drive. It basically goes through three fundamental stages. First, that pure AC supply comes in and gets converted into a DC supply using a rectifier. Second, it just kind of hangs out in what we call the DC link. And third, that DC is converted back into AC using an inverter. Now, it's this third step, the DC back to AC conversion, where all the distortion happens. So our primary focus today is going to be exclusively on this final stage. Moving on to Section 2, meet the IGBT switch, the engine of the VFD. Right smack in the middle of that final inverter stage, we meet our prime suspect in this whole mystery. It's called the IGBT, or insulated gate bipolar transistor. Basically, it's a power electronic device that is primarily responsible for varying the motor's RPM to match exactly what you require. Think of it as this hyperactive, fast-switching gatekeeper that is rapidly turning power on and off to dictate the final output. It's doing all the heavy lifting. Now, what's really interesting about this is just the sheer scale of the speeds we're dealing with. It is honestly staggering. In a standard fundamental frequency, the on and off operation happens about, 50 or 60 times a second. And that seems incredibly fast to us, right? But when the IGBT steps up to convert that DC back to AC, it executes this switching operation thousands of times in a single second. Thousands. It is a massive, massive contrast in speed. Which brings us to Section 3, the PWM illusion, macro versus micro. So this mind-boggling speed, it isn't just a fun engineering trivia fact. It literally fundamentally alters the physical nature of the electrical current. This is done through something called PWM, or pulse width modulation. Basically, it's a technique where switching devices trigger multiple rapid pulses, again, thousands of times a second, to simulate a waveform. Because the IGBT fires off so unbelievably fast during that DC to AC conversion, the final alternating current isn't a continuous flowing river of electricity anymore. Instead, it is actively being built out of countless tiny, sharp pulses. And this creates a really fascinating macro-level illusion. If you step back and look at the whole system on a large scale, the overall output perfectly mimics the smooth, rolling curve of a traditional sine wave. From a distance, it looks perfectly normal, completely undisturbed. Let's move in closer and see how this builds, because when you zoom in on the micro-reality, the entire illusion just breaks down. Those thousands of fast IGBT triggers mean the wave is actually made up of these rigid pulsed blocks. It's absolutely not a smooth line at all. It's just thousands of tiny continuous square pulses roughly stitched together. What you are seeing is the actual physical evidence of that switch snapping on and off thousands of times a second. And boom, right there is the answer to our missing sine wave mystery. It is exactly this rapid, continuous triggering that introduces disturbances and harmonics into the electrical system. You simply cannot rapidly chop a DC signal into thousands of tiny pieces to simulate an AC wave without creating some electrical noise. The sheer violence and speed of that switching permanently distorts the wave. So a pure sine wave? It's physically impossible to get at the output. All right, let's wrap this up with Section 4, the perfect interview answer. Nailing the VFD question. This missing sine wave mystery is actually one of the most common and frankly tricky interview questions for electrical engineers. So the crucial point is to walk your interviewer through the logic step by step. First, confidently state that the IGBT is a fast-triggering power electronic device. Second, explain that it switches thousands of times per second using PWM. Third, point out that this extreme speed inherently introduces harmonics and disturbances into the system. And finally, bring it home by concluding that the result is a simulated, distorted sine wave, never a pure one. Answering like this perfectly shows you understand not just the what, but the why. Which leaves us with one final, pretty provocative thought for today. We've officially solved the mystery of the missing sine wave. We know the VFD chops the current up, completely distorts it, and sends this jagged, harmonic-heavy signal down the line. But how does the motor actually handle all those rigid pulses and harmonics without just tearing itself apart? What exactly happens when that highly distorted wave hits the coils? Well, I'm going to leave you to ponder that one, right up until we tackle the next piece of this incredible engineering puzzle.